I saw the sign, and it opened up my eyes. I saw the sign. Life is demanding. Without understanding, I saw the sign. These powerful words were made famous by Swedish pop group Ace of Base, whose repetitive reggae-influenced masterpiece, The Sign, would take home Billboard's 1994 Song of the Year award. But what is a sign? A very good pop song? Absolutely. A bright red octagon used to direct traffic? Sure. A picture of a little guy slipping so you know a floor is slippery? They're all signs. Okay, put simply, a sign is an agreement. An agreement between sender and receiver. A piece of information put out into the universe with the intent of being understood by the information seeker. Today on Mr. Wood's World, signals. What is up, guys? Happy Tuesday. Happy Tuesday, 31st of March. Last day of March. What a year this month has been. Remember March 1st? Remember that day when you could go out to eat and they were still making new episodes of Jeopardy? There was no such thing as a toilet paper reseller. Simpler times. All jokes aside, I do want to say that I am very proud of you guys. This is a really difficult situation, and you guys have been handling it with grace and aplomb. There's a silent B on that word, so watch out. If you guys haven't had that in vocab yet, here, I'll bring it up. Aplomb. Self-confidence or assurance, especially when in a demanding situation. Let me make sure I pronounce that one right too.
Aplomb.
I'm a genius.
Aplomb.
As I kind of just demonstrated, this is an audio format, but I can display visuals here. Here is a baby octopus, which I bet you didn't even know were cute, but they sure are. Look at that, they sit right on the tip of your finger. Unfortunately, not as cute when they get older. More nightmarish. Have you guys ever seen that video? Have you guys ever seen the video where it's the octopus squeezing out of like a quarter-sized hole on a boat? It's creepy. Let me find it real quick. Hold on. You could make the argument that is science. That's science related. But we're not talking cephalopods today. Cephalopods. I must have gotten a good night's sleep because I'm just crushing it with words today. We're not talking about cephalopods, we're talking about signals and information. So as we discussed, for any signal to be understood, there needs to be an agreement between the sender and the receiver about what that signal means. Examples would be the chime of a doorbell. It's kind of universally understood that it means there's a guest at the door. Or a traffic light. We know what green, yellow, and red lights mean, what they symbolize. We know that from childhood. Signals like these can be easy, but there can be complex signals too. Which brings us to the 1800s, where people would communicate with electric signals, and there was a fella by the name of Samuel Morse who patented a version of the electrical telegraph. If you guys have not seen a telegraph, It's kind of like if you were communicating with just a computer mouse or like a computer with one key. So how do you communicate with a device like that? The answer is through electrical signals, vocab word. Electrical signals are information that is sent as a pattern in a controlled flow of current through a circuit. So Samuel Morse helped develop the Morse code, which you guys might have heard of. It sounds like this, and it looks like this. I expect all of you to have the Morse code alphabet memorized by the next time we meet. Your next test will be in Morse code. Okay, Morse code is a combination of short and long wave pulses that stand for letters of the alphabet. Now, a wave pulse is a pulse of energy that travels through the circuit when it is closed. Now, this is reliable, but it is very slow. I don't want to spoil the story of the Titanic for you guys, but they used Morse code, and it didn't work out for them. There was also a ship, the Californian, who earlier in the day told the Titanic through Morse code that they were ahead of them, and they were like, there's icebergs everywhere, be careful. And the guy on the Titanic responded, shut up. That's real. It always makes me kind of laugh. So Morse code, all the rage until about 1876. That's when a little guy known as Alexander Graham Bell burst on the scene and patented the telephone. With a telephone, two people spoke into devices that were part of the same circuit, and they could talk to each other. A microphone would convert sound waves from the air, so your voice, into electronic signals which were carried to a receiver somewhere else. Back then, there were literal switchboard operators. You might have seen this in movies, but it would be these people that would manually connect two telephones to the same circuit. You guys might have also seen these things outside. They're called telephone lines, and they used to connect you to phones in other people's houses. As a 58-year-old man, I remember having to call my freshman formal date on the phone to ask her to the dance. So I had to call her house, talk to her mom, then ask to talk to her. Brutal. It was brutal. Now you guys just send a text that says, freshman formal? And the other person sends like a cowboy emoji, and the interaction is over. I'm wildly jealous. I should also note that I got my braces off the day before freshman formal, and I looked great. Moving on, let's talk about electromagnetic signals. So this is information sent as patterns of electromagnetic waves, such as visible light, infrared waves, microwaves, and radio waves. Electromagnetic signals have electronic signals beat. They are way faster, and they don't require wires. And when I say they are way faster, I mean electromagnetic signals travel at the speed of light, which is much faster than the speed of an electric current. Electromagnetic signals launched wireless technology, your cell phone, your television, even like a walkie-talkie uses these signals. And these types of technologies, look around. I mean, they can currently dominate the telecommunications industry completely. So let's talk about two kinds of signals, okay? Analog signals and digital signals. Analog signals allow for a continuous record of some kind of action. This is the advantage of an analog signal. They provide the highest resolution of an action by recording it continuously. An example would be a seismograph. They measure seismic activity from the earth, like earthquakes, okay? But the disadvantage is that it requires ink and paper, and it can be easily damaged. Analog signals also take up a lot of space. Think of all the paper that a seismograph would produce, or think of a vinyl music collection versus a 1 terabyte hard drive that the entire collection can fit inside. Now, a digital signal allows for a record of numerical values of an action at a set continuous time interval. So a digital seismometer can record seismic activity on a second-by-second basis and assign the ground motion numerical values
produce a list of numbers that chart seismic activity. The disadvantage of this is you have no record of what occurs between those second-by-second recordings. Now, if you are like Mr. Wood and you heard all this information, there is currently a monkey banging cymbals and doing flips in your brain. But I think it makes way more sense when you look at this chart from the book. And this might only be in the teacher's edition, so I'll snap a pic and put it in here. As you can see, the red line is like the analog signal. It's smooth and continuous, while the digital signal is a series of sharp increases and decreases. And you can kind of visualize how one would be more reliable than the other. And the way we can make the digital signal more reliable is by increasing the rate at which we sample the information. You see, it starts to resemble the other graph more. So let's just wrap up with that idea, sampling rate, which is how often a signal is recorded or converted to digital code. The more data captured, as we saw in that graph, the recorded information is more detailed and realistic. If you think of a music file with a high sampling rate will sound great. It's rich and clear and clean. And music files with low sampling rates, they don't sound so great. So, the higher the sampling rate, the more intervals you gather information at, the more detailed and realistic and better that information is going to be. So we can stop there for today, guys. We learned so much about signals and the Titanic today. If you guys want to learn more about the Titanic, there was a movie about it. It came out, I want to say, in the early 1970s. And it was a double VHS tape, so you know it was legit. Say what you want about Leonardo DiCaprio's acting, okay, but the man is a star. Sorry, ladies, I know Timothy Chalamet is your champion, but he couldn't pull off Titanic. Timothy Chalamet looks ill. He looks sick all the time. I want to give him soup. He's got too many E's in his name. And he's light as a feather. If he was on the deck of the Titanic, he would simply blow away. Okay? There's a few pages left in this lesson. If you guys want to read ahead, go for it. We will try and go over them on Thursday. In the meantime, just keep up the good work. Let me know if you need anything. You know, have a good one, guys. Mr. Wood, out.